So our second exam will be on the 14th. This is actually a fast unit. So a week from Wednesday will be our second exam. I'm almost done with the lecture. I'll be with the unit. I'll be done with the unit on Wednesday. So the exam will be on chapters 26 through 28. There's a capacitors worksheet to do Wednesday. Just upload it on the Canvas. And then I added 2 more days to the Ohm's Law lab, which is due on the 11th. I sent you folks a copy of a sample lab and what a lab report should kind of look like. And I expect you all to ask me questions on Wednesday regarding the labs. And I'll talk a little bit about what I expect from it. I've said some last Wednesday, but I just want to say some more. And then homework 5 is due on the 6th. Okay, so these are your reminders. I've been looking at the video lab reports, and a lot of folks did a nice job. I'm actually grading the multimeter quiz first, just because it goes faster. I just have one more lab section to complete, and then I'll be done, and then I'll post the grades. And if you did everything that you're supposed to do in the lab, then you got full credit. Some people skipped a part, or for some reason, or maybe accidentally skipped a part, so I had to take off points for that. But overall, they look nice. So what I want to do today is, I didn't write it down. I want to focus on an example of series and parallel circuits. Actually, a couple examples. And I want to do Kirchhoff's laws. Okay, so that'll be my focus for today. And then on Wednesday, I'll finish off the unit with RC circuits. So last time we finished off talking about series and parallel circuits. I did a demo with the light bulbs. And today I just want to do some examples. So, or I want to start with some examples. So on the board, I kind of summarized really the equation you need to know for doing series parallel circuits. You only need those 3 equations. And I want to do an example that's really both series, that has a combination of series and parallel resistors. So here's the example. And again, those resistors could represent either a simple resistor that obeys Ohm's law, or they can represent some load, like a light bulb, etc. Basically something for which you can calculate the resistance. So what I want to do in this circuit, I want to calculate the equivalent resistance of the circuit. And then I want to calculate the voltage across each resistor and the current through each resistor. In fact, I also want to calculate the power dissipated by each resistor. And my approach will be very similar to the problem I did on capacitors. So I'm going to take this circuit and reduce it down to a single resistor. In the problem in the previous chapter, I took the circuit and reduced it down to a single capacitor. So essentially I'm doing the same thing. So when I look at this, I can right away see something I can reduce into one resistor. Which one? Anybody see what I can reduce right away? Yeah, the 2 in series, the 2 12s. Those 2 12s add to a 24 kilo ohm resistor. And I try to choose a number so they're nice, so we can do the math, most of the math in our head, okay? So 12 plus 12 is 24. So now I have a 24. Yeah, I mean the 5 and the 9K will be in series, of course, but I have to reduce the 8 and the 24 into one resistor. Then I'll have 3 resistors in series. So we'll get to that point, Patrick. So we have an 8 and a 24. And so, okay, I got to do a little bit of math. I know they're in parallel. We're going to do some fractions with common denominators. Okay, so I have a 1 over 8 and a 1 over 24. 24. I want to get a common denominator, which should be 24. So this is 3 24ths. I take the reciprocal of that, and I get 6 kilo ohm. So I replace those two with a 6 kilo ohm resistor. Now I have the 5, the 6, and the 9 in series. I add those up. 5 plus 6 is 11. 11 plus 9 is 20. So now I have 20 kilo ohms. So that's my total resistance. And so I draw my final circuit. So each time I reduce, I combine resistors, I actually redraw the circuit. And the reason why is because I want to start working backwards to figure out current, voltage, and power. So let's do that. So because the resistance values are in kilo ohms, my current values, if I just take 10 over 20, the units will be milliamps. Does that make sense? I'm automatically going to get units of milliamps if I just do 10 over 20. 10 over 20 is a half, so I get half a milliamp. So the current that's delivered by the battery is half a milliamp. Which I've drawn there. Well, I have 10 volts across that. I have 10 volts across that resistor, it's 20 kilo ohms, half a milliamp. Power is V times I, or delta V times I. 10 times a half is what? 5? So 5 milliwatts are being dissipated by that resistor. Are we okay so far? Now as we go through this circuit, we know that the current through each one of the resistors is going to be equal. Oh, power is just delta V times I. So let me go up to on the board. So power, I'll write it down here. Is delta V times I. Of course, if I use Ohm's law, I can rewrite it this way, or I could rewrite it this way. Okay, so my delta V is 10 volts, my I is 5 milliamps, so 10 times a half is 5. That's 5 milliwatts. Are you okay with that? Okay, cool. And we could have taken I squared R, I got to get the same thing. So each resistor has half a milliamp going through it. So I can calculate the voltage across each resistor. So for example, let's do the easy one. 6 kilo ohms times half a milliamp. Remember, a milliamp has 10 to the minus 3 amps. kilo ohms is 10 to the plus 3. So those are going to cancel out when I multiply them. So 6 times a half is 3. So there's going to be 3 volts across this resistor. This 5 kilo ohm resistor, if you take that 5 kilo ohms and multiply it by half, 5 times a half is 2.5. So I have 2.5 on the top resistor, 3 on the bottom, on the middle resistor. That gives me 5.5. I better have 4.5 left over to give me 10. And if you actually multiply 9 by a half, you will get 4.5. And stop me if I'm going too fast. I chose the numbers to be simple so I can do it without really going on the board. Are we okay with that so far? Okay, I'm hoping the answer is yes. So the last thing to do then is to calculate the power dissipated by each of the resistors. So I can either use delta V times I. Oops, let me magnify this, sorry. I can use delta V times I squared R, or delta V squared over R, either one, to be able to calculate power. I can just take delta V times I. So 2.5 volts times a half of milliamp. That should give me 1.25 milliwatts. And I did round these off, so I was being careful with sig figs. If I take 3 volts times half a milliamp, I get 1.5 milliwatts. If I take 4.5 volts times half a milliamp, I get 2.25 milliwatts. Are we okay with that? Everybody following? Okay. So the 6 kilo ohm resistor replaced an 8 kilo ohm resistor and a 24 kilo ohm resistor. And since they were in parallel, they have to have the same voltage across them. So the 8 kilo ohm resistor has 3 volts across it, and the 24 kilo ohm resistor has 3 volts across it. So we already know the voltage, so all I got to do is calculate the current. So here's the stuff reviewing everything. So both of these resistors have 3 volts across them because they replaced that 6, or the 6 kilo ohm resistor replaced these two. So 3 for this guy, 3 for this guy. So all I got to do is take 3 divided by 8,000 to calculate this current, and then 3 divided by 24,000. 3 over 8 essentially is 0.375. Okay. And 3 over 24 is an eighth. So it's 0.125. Does that make sense? And again, I can calculate power. Power is my 0.38 milliamps times 3 volts. And then my 0.12 milliamps times 3 volts. And that gives me 1.1 millivolts and 0.36 millivolts. If you add them together, taking into account the sig figs, you should get the 1.5 milliwatts. Because remember, these two resistors these two resistors were replaced by the 6 kilo ohm resistor. Are we okay so far? All right, so that 24 kilo ohm resistor replaced two 12s that were in series. So that means the current through each one of those two resistors in series has to be the same, 0.12 milliamps. And the voltage will be shared amongst each of the two. The voltage shared between the two is going to be 1.5 volts. They have the same resistance. So each one will have 1.5 volts. Each one will have 0.12 milliamps. And the total power dissipated will be 0.36 milliwatts. So each one's going to dissipate 0.18 milliwatts. If you take 1.5 times 0.12, you get 0.18. So basically, I know everything about this circuit now. Okay, so this is an example, you know, you have a couple of problems like this in the chapter 28 homework. So when you look at the problems, there's going to be a lot of blanks to fill in, but the problems don't take very long to solve. Just that you can get a lot of information from these circuits. One of the problems in the homework might have 20 blanks for you to fill in, but you can do the problems right away, like we did this one. Of course, I chose the numbers to be really nice, so I didn't need a calculator. Okay, so far? It's not both, it's each one, and that should be each one is 0.18. Okay, yeah, I should have written it as 0.18. It is confusing. Sorry about that. All right, so I want to do more series parallel examples, and I don't like doing the ones that are either series or parallel, because those are boring. At least to me, they are. So I want to do something that's a combination of the two. So this is called a Wheatstone Bridge, which is used to measure current. I'm sorry, to determine resistance of an unknown resistor. Because now we have multimeters that do that for us. So we basically don't use this technique. We don't use this technique as much anymore. So I have this circuit with 4 resistors, and I put an ammeter between points 1 and 2. And I want to know the condition on the resistances so that no current goes through the ammeter. Okay? And I noticed that my internet's a little bit unstable. I apologize. I'm cutting out, I think. Sorry about that. So, but I'll continue, because what I'm recording at home is... So, okay, let me rephrase then. So, I want to hook up this circuit. I want to find the conditions on the resistors such that no current goes through the ammeter. So let me draw the circuit. Now, I'm going to assume the ammeter is ideal. What does that mean? What does it mean if the ammeter is ideal? Yeah, the ammeter has no resistance. Okay, good. A bunch of you chimed in on that one. Good. So we're going to assume the ammeter. So basically, there's no. That means 0.1 and 0.2 are at the same potential. Well, actually, I should say either way, they're going to be at the same potential. But assuming A doesn't have any resistance makes the analysis much simpler. Okay, so let me draw the circuit. Okay, so here's the ammeter. So Here's point 1 and point 2. Since basically all I've done is connected those 2 points together with a wire, V1 has to be equal to V2. Isn't that true? Because all I've done is connect them together with a wire. That's really all I've done. If that's the case, then isn't it true that delta V of RA is equal to delta V RB? Because both resistors have the same potential here, and then both resistors are going to have the same potential here. So the drop is going to be the same on both. Does that make sense? And in fact, then the drop from here to here and the drop from here to here are the same. Furthermore, I can write these in terms of I can write them in terms of current times resistance. So far, so good. What can I say about IA and IC? Since no current, since all the current goes, there's no current that goes through the ammeter, all the current goes like this. What can I say about IA and IC? Well, they're the same thing, right? Well, the condition we want to find the conditions on the resistor so that no current goes through the ammeter. Okay, we're already saying there's no current. That's the condition. That's what we're solving for. Okay? We're solving for the conditions on these resistors so that no current goes through here. If we don't satisfy that condition, you're correct. Current will go through the meter. Okay, but I said it ahead of time that no current goes through A. Okay, that was the condition. So these two currents have to be the same because the current's going to go like this. None of it will go this way based on our initial condition that we set in the problem. So this is an IA. Can I do the same thing about B and D? Current's going to do this. So that means this is IB. What if I divide the equations? I divide the equations. If I divide the equations, I get R sub A over R sub C equals R sub B over R sub D. That must be the conditions on the resistors so that no current goes through the ammeter. Yeah, we can do that, Patrick, too, I guess. Well, if we put a wire, then there's no way to sense there's no current, right? What people do, what they would do using this technique, they would put two known resistors here, and they would put a resistor you can change here and an unknown here. And by varying this resistance until you get no current through here, you can determine this value. And that's what this circuit was used for. For a long time. And in fact, I remember I taught a lab at Sac State, and they might still do that lab. They have a very sensitive version of this for measuring low resistors. The only problem with your ammeter is you got to make sure this has a very low resistance. So when you get to really low currents, when you set the ammeter for really low current, its resistance increases. If you put a voltmeter between these 2 points, and let me think about what the voltmeter. I guess you could. I guess you can use a voltmeter. The ammeters, they use something really. It's not really an ammeter. It's called a galvanometer, which is more sensitive than an ammeter. So in the case of a galvanometer, what happens is if a current runs through it, there's a torque on a coil, and it makes the coil rotate. Yeah, it's really a galvanometer, to be honest. Okay, so basically a galvanometer, just if you run a current through a coil, you can get a dial to rotate. Of course, we got to talk about that in the next chapter. When you have a current through a coil, you'll get a magnetic. If you run a current, you'll get a magnetic field. And if you put a coil in a magnetic field, the coil will want to rotate. So actually, a galvanometer is more sensitive, and in reality, that's what you use. Are we okay with this? The wire can't measure anything. That's the only difference. You're right, you can put a wire there. You can treat it like there's a wire there. That's true. It acts the same, it's just that the wire doesn't measure. The wire doesn't measure anything. Okay, so this is the condition, and you can use this to measure resistance. And yeah, this really should be a galvanometer. Okay. Anyway, I'm recording at home too, so if the internet version, if the Zoom version is not clear, at least mine will be when I put it up on YouTube. So I want to do a different problem. I'm going to look at the case when this condition is not met. Okay, so let's assume in the next example that this condition is not met. So now, if this is the case, you will get current going through here. How much? Okay. So let me put some values in. Let's set the power supply voltage, I'll use red, to be 300 volts. Okay. And let's set RA be 3 kilo ohms. We'll let R sub B be 6 kilo ohms. and C and D will be 2 kilo ohms. I want to know how much current actually goes through here. Okay? So let me redraw the circuit without the meter, because you guys want to put a wire in there. I'll do that for you, okay? I'll replace it with the wire. And I drew it too small. Hold on, let me make it a little bit bigger. It's still true that these 2 points are at the same potential. Just 1 second. Okay, good. Okay, so it's true that these 2 points are still at the same potential because I just have a wire there. Strange, I don't hear any sound, so I'm hoping. Okay, just give me a second here. Okay. Okay. How are these two connected? They're in parallel, and these two are in parallel, right? So I had these two in parallel and these two in parallel. So let me redraw the circuit. These two in parallel, it's easy to figure out the equivalent resistance. What do you think it's going to be when I combine these two? These give 1 kilo ohm. And do I have to do the math for this one? 1/6 and 3/6? I get a common denominator. I take the reciprocal, I get 2 kilo ohms. Okay, so my total resistance in my circuit is 3 kilo ohms. What's 300 divided by 3,000? .1, so 0.1 amps, 100 milliamps. I'm going to write it in green. Hopefully you can see that. What's the voltage across each resistor? Well, it's going to be 200 volts. $100 volts. I'm sorry. I went a little bit faster. Why are isn't it true these two are in parallel? And these two are in parallel? And then these two combinations are connected together. They're at the same point, right? I went too fast for getting the values? Okay. So I'm going to take 1 over 2 plus 1 over 2 gives me what? What's 1/2 plus 1/2? 1. Okay, so that gives me 1 kilo ohm. So these two give me this guy. And this one's 1 over 3 kilo ohms plus 1 over 6 kilo ohms. You get a common denominator of 2/6. 2/6 plus 1/6 is 3/6. The reciprocal of 3/6 is 6/3, which is 2. So then I have 2,000 times 0.1 is 200. 1,000 times 0.1 is 100. The total current is 0.1 because if I take 300 and divide it by 3,000, I get 0.1. Is that okay? I hope. Okay. Okay, all right, sorry. So I have 200 volts across this one, and I have 200 volts across this one. I want to find the current through this one. I got to take 200 and divide by 3,000. So the current through this one is that's this current. And if you do this on a calculator, I mean, you know 2 over 3 is 2/3, right? So this current is going to be 66.7. I'll use a darker color, sorry. I'll use black. 66.7 milliamps. Then for this one, I take 200 divided by 6,000. 2 over 6 is the same thing as 1/3. So let me draw it here. And I guess I'll make it purple. So current's going this way, 66 milliamps hits this node. I got to figure out what's coming here and what's coming here. So both of these are 2 kilo ohms. They both have 100 volts across them. Okay? So I'm going to take 100 volts over 2,000 ohms. That's 50 milliamps. So I'm going to have 50 milliamps right past the junction. So I have 66 coming down here, 50 going here. Where's the rest going? I got to use the junction rule. If 66 go here, 50 is at the bottom, 16.7 have to go through here. Yeah, 16.7 goes through the ammeter. Remember, charge has to be conserved. So, I mean, just think of water flowing through a pipe. If you have less water going here than here, then some of it had to go that way. Now, let's see if this if this is consistent, because I got to get this same agreement on this side. I have 33 going into this junction, but then I have more coming out. Why do I have more coming out? Where's that coming from? That's coming from here. It's coming from what's coming through the meter. Yeah, it's a 16.7. If you take 16.7, add it to 33.3, you get 50 milliamps. It better be consistent, right? It's conservation of charge. Does that all make sense? Okay. I'm sorry if I did some of the math too fast. Sometimes when the numbers are simple, I could do the math pretty quick. We all right with this then? Okay. What's nice about videotaping is you can play this over and over again. All right. How about this one? This is a fun circuit. And different people have different ways of viewing it. And so there's a lot of folks that are way better than I am at analyzing these type of circuits. But let me tell you how I look at it. Let me redraw this first. Three resistors. I tie them together. And then between this point now what? Well, this is what I would do. And again, different people can view it differently. Let me put in some values. By the way, I forgot to put in the values. Yeah, well, this is what I would do. Okay, let's say this is 100 volts, and this is 0 volts. That tells me that this point is 100 volts. What is this point at? It's at 100 volts. Why? Because we're assuming the ammeter is ideal. Okay, so if this point is at 0 volts, so is this point. And then what about this point? Right, they're tied together. What's the voltage drop across each resistor? $100 volts. So the current goes here and it splits. Where's the ammeter? There's a 100 volt drop here. Yeah, it's supposed to be for this. So there's the ammeter's over here. So how much current's going through each one? Well, let me ask this. You have 100 volts across each one, right? A 100 volts across each resistor, but what's the current through each one? What's the 100 divided by 1,000? It's 100 milliamps, right? How much is the battery delivering? Well, it's 100 plus 100 plus 100. I think it's faster for me to do it that way than finding the equivalent of resistance. So if 300 goes here, 100 goes this way, 200 goes this way. Of course, you normally don't hook up a circuit like that. The point of this problem is to show you how, to get you to understand circuits. There's a program, and I don't know if you and I might have to put this on Canvas if I have it. When you first took Physics 205, you had a physics software folder. And I don't know if you were all able to take all the software from the folder. One of them was an old version of a program called Circuit Maker, and I made this circuit using Circuit Maker. It also allows you to actually simulate that circuit. So if you don't have it, I'll try to look for it and I'll try to put it up on Canvas. The only problem, I'm sorry, what is the little component? Oh, you mean this one? That's just the ground. That represents ground. So I have a reference. One point is 0, the other point's 100 volts. When I do this in Circuit Maker, when I made this in Circuit Maker, I had to put that ground in there. So anyway, if I find Circuit Maker, and it might not work on the newer computers, I'll try to put it on Canvas. And you can play around with it, and you can build your own circuit and analyze them. A couple more things before I get to Kirchhoff's laws. I want to talk about internal resistance. Any power supply has an internal resistance associated with it. It doesn't mean there's a physical resistor there. It behaves as if there is a resistor in series with the power supply. In the case of a battery, it's due to chemical processes, that internal resistance. In the case of a power supply, it's mechanical or electromagnetic. Typically, you want that to be small. And analyzing a circuit with an internal resistance is actually not hard because all you have is a little resistor in series with your load. Sometimes the wording in describing these kind of gets in the way of understanding. So here's a power supply or battery, and here's my internal resistor, R. This is the load. I'll just put R. This is your load. This could be a light bulb or whatever. Okay. And you're given the EMF of the battery. That's the rating that you get on the battery itself. Okay. And we put a dotted line around it to indicate this is all inside the power supply or battery. The amount of current that is really going through the circuit is going to be your EMF divided by the total resistance. So your total current is going to be the EMF divided by the load resistor plus the internal resistance. And of course, as this gets bigger, like on a battery, then your current gets lower, and then at some point, the current will be too low to turn on this bulb, if this were a bulb. Now the voltage across the load is going to be this current times that resistance. This is also, it looks like, you can think of it as a voltage divider because a certain percentage of the voltage is across this guy and a certain percentage of the voltage is across this guy. You want most of it to be across this guy. And what is the effect of the internal resistance? And if you have a big enough current, you can see the effect. So if you go in your car, turn the headlights on, and then if you have a gas-powered car. I haven't tried it on an electric car. You turn the key. I guess you would see the same thing in an electric car. You turn the key. Right, now you're running a lot of current to start up the car. The voltage across this guy will be much higher, and you'll see your headlights dim. That's the effect of this. Okay. Question I want to ask is, what should the relationship between little r and big R be so I can maximize the energy to the load? I want to maximize the energy transfer to the load. So the power is going to be delta V sub R times I. If I multiply these two together, how am I going to maximize it? How do I figure out how I'm going to maximize that? Thanks, Patrick, about your comment. How do I maximize this? So I take the derivative of this. And I forget the quotient rule, so I'm going to write it this way. So here we go. I'm going to take derivative. And people complain, I always forget this term, and there's a reason why. So I want this thing to be 0. I don't care about this term, okay? So I'm gonna, that term is meaningless to me. I want this term inside the brackets to be 0. Let me rewrite this. I get a common denominator. And let's see, let me keep going. Let me simplify the numerator. So what's the relationship between little r and big R? That's when you get maximum energy transfer to the load. And we used to do a lab. We used to do a lab on this. Just to show that. Okay. We okay with that? You get a similar problem when you do AC circuits, except it's not the resistances, it's called the impedance, and we'll talk about impedance towards the end of the semester. Okay. So a couple of questions. How are devices connected in the house? Yeah, they better be parallel, right? You don't want your air conditioner connected in series with your lights. That would be bad. Or your computer connected in series with the lights. That would be bad. Okay. What about the circuit breaker, or in the old days, the fuse? How is that connected in your house? Yeah, in series. Because what you want is, you want that circuit, once that circuit breaker goes off, you want everything else to go off after it. So it has to be in series. And you saw that in the multimeter quiz when if you had two bulbs in series, you took one out, everything went off. In the old days, they used to have a fuse. And some people would actually put a penny in the socket. And guess what happens? It's tore out of those homes. That was the old days. That's one of the reasons why they got rid of the fuse. The other reason is once the fuse is gone, then you got to replace it. Circuit breaker just trips, and then you can reset it. Okay. By the way, your multimeters, the 10 amp scale is not fused. So be careful with those. What's the purpose of grounding? I'm asking you folks practical questions, right? Regarding what you experience in your house. Yeah, it's safety. In the old days, a long time ago, there was no grounding prong. So if the chassis of let's say a washing machine, let's say it was a short and the chassis of the washing machine now is at a high potential and you touch it, guess what happens to you? You get killed. People used to get killed from them. And so they came up with the idea of the grounding. So now they ground the chassis. For example, let's say I have a washing machine. If there is a short and you touch it, you have a higher resistance, so the current won't go through you. So that's a safety. That's a safety thing. We talked about this already. So anyway, what I like about this is there's a lot of practical. There's probably a lot of practical things regarding things in your house. For example, when you plug things into your socket, you can't just plug all kind of stuff into your socket, right? Imagine plugging in 2 vacuum cleaners. I've seen people do that. Plug in, let's say, 2 vacuum cleaners into a socket. If they're the old vacuum cleaners and you turn them on both at the same time, guess what's going to happen? You're gonna trip the circuit breaker because you're drawing too much current. Okay, the sockets are 20 amps. Yes, I've done that, and I'm going to bring up that example, Justin, when I talk about Faraday's law, because that's electromagnetic induction. And that's a high voltage you're producing when you do that. Okay, so let's do one more. And I thought I would have started on Kirchhoff's laws, but I got another example here I want to do. I want to analyze this circuit. I want to know the current in this circuit. And really, this is a prelude to Kirchhoff's laws. I have 2 batteries and 2 resistors in my circuit. So the bottom one's 9 volts. So, yeah, it looks weird the way I've hooked up the batteries here. So this is what I'm going to do. The easiest thing for me to do is use Kirchhoff's laws. I'm going to use the voltage law, which says that the sum of the drops in a loop is 0. Yeah, the total voltage will be 10.5. So I'm going to assume that the current is clockwise. If I'm wrong, then when I solve my problem, I'll just get a minus sign. That's no big deal. And what I'm going to do is sum voltage drops. So I'm going to start here and go clockwise. I go from a lower voltage to a higher voltage. Is that a drop or a gain? It's a gain. So I say plus 9 volts. So now the current goes to the resistor. Remember that J equals sigma E. That the current is in the direction of the electric field. And the electric field, it points in the direction of decreasing voltage. So that if I go this way, if I count this way, then my voltage drops. I get to this one, and again, I'm going in the direction of the electric field, so the voltage drops. And now I go from a lower to a higher. That's a gain. So I get 9 plus 1.5 is 10.5 volts. And in the interest of time, I'm going to move both of these to the other side of the equation. Okay, that's it then. Let me check my time. Okay, I got some time. So I use the loop rule. How did I know I could have everything like that? Which part, Morgan? The first line. This first line. So Kirchhoff's loop rule, we talked about the sum of the delta V's equals 0. That's a true statement. This is the voltage rule or voltage law that I talked about earlier when I did the resistors in series. It's always true that the sum of the voltage drops equals 0 because of this. The electric field is conservative. Yeah, so when I do this, I know that the current is going, I pick the current that direction, right? I pick the current to be clockwise. The current is in the direction of the electric field. I should say the electric field is in the direction of the current. So electric field's that way. I'm summing in the same direction. And the voltage drops in the direction of the electric field. Okay? So if I go this way, the electric field points that way, then I know the voltage is dropping in that direction. If I'm saying the current is up here this way, I'm saying the electric field is in that direction. And if I sum in that direction, then the voltage has to drop in that direction. Yeah, these two are just changes in the voltage. If I summed in the opposite direction, if I actually did a sum in the opposite direction, then these would be positive and these two would both be negative. It would be as if I took this equation and multiplied by -1. And the thing you should notice is arbitrary whether I do this clockwise or counterclockwise. It doesn't matter. Because if I sum the voltages counterclockwise, then it would just be as if I multiply that thing by the equation by -1. We okay? Yes? No? Oh, okay. So, okay, let me do that then. If I say the current this way and I sum that way, I go from positive to negative, right? Isn't that a drop? And then when I reach this resistor, I'm going against the direct, because I said the current's this way. I defined the current to be that way. So isn't it true that if I go against the direction of the field, the potential increases? It's because of this. So that would change all the signs. All it does is changes all the signs. So it'd make this positive, and it would make this positive, and it would make this negative. Because then if I go counterclockwise, I go from positive to negative. It's a drop. Yeah, I would just be going against the electric field if I went counterclockwise. So now the fun thing is to ask, go back to the Wheatstone Bridge problem and ask, how in the world do I solve that one? How do I solve that? It's neither series nor parallel. Turns out, because series or parallel only works for series and parallel, but what if I have a circuit that's neither? Well, it turns out then I can use Kirchhoff's laws. Kirchhoff's laws, I can use it for any case because they're general rules for any kind of circuit. And so what I'm going to do is apply Kirchhoff's laws for this circuit. Remember what the laws are. The sum of the voltage drops around the loop is 0, and then the sum of the currents entering a junction equals the sum of the currents leaving a junction. Or you can just say the sum of the i's equals 0. So how do I apply these rules to this problem? Actually, how do I apply the rules to any problem? So let me say a couple of things about the rules. So what we're going to be doing, I'm going to say it this way. In this course, we're going to be doing these kind of problems using Kirchhoff's laws directly. When you take Engineering 17, Yeah, you'll fix it. You'll be able to do it now, I bet. When you take Engineering 17, you will learn tricks based from Kirchhoff's laws that it will allow you to simplify these circuits very quickly. There's actually a trick for this one too. Okay, but you'll learn them then. So you learn the tricks then. So everything we're doing here is by brute force. So we're going to do everything the long way, and then in Engineering 17, you'll learn tricks for various types of circuits. Okay, so I'm just teaching you the general way of solving a problem, and then Pat and Gail will teach you all the tricks to these. Okay. So we're going to use Kirchhoff's laws, and I have extra notes here, and to be upfront, the book where I got these ideas from, because they do it the best, they treat this topic the best, is a book by Young and Friedman, whatever edition you use. They use the best, to me, the best technique to solve these type of problems. Because when I learned it, to me it was confusing when I learned it. But the way they teach it in their textbook is great, at least to me. Okay? And I'm not going to be able to solve the problem in 7 minutes, but I'll talk about it, okay? So you're going to use these laws, or rules, whatever you want to call them, that you see them called laws or rules in different books, to solve this circuit. So what is the process? Okay, what is the method of approach? First, you got to draw a large picture. Okay, you got to draw a picture large enough so you can draw in it. Because if you draw teeny tiny pictures, you're not going to be able, you're going to get a mess. So you want to draw a nice big picture. Once you've drawn the big picture, you want to apply the current rule right away. The idea is to figure out how many types of independent currents are there. And you'll see what I mean when I talk about the example. How many currents are independent of each other? And then choose a loop and pick a direction to sum the delta V's, just like I did in that one simple example. See, the number of independent currents is going to tell you how many loops you're going to need to solve the problem. You go around the loop adding delta V's as you cross them. Choose loops until you have as many equations as unknowns. I have additional notes in here. I'm going to skip a lot of that. You can read through to help you with the technique. Like I said, this is all from Young and Friedman, and I just like the way they treat this. And then you're going to solve simultaneous equation. In my class, the most unknowns you'll have is 3. When you take Engineering 17, you might have 6 by 6s to solve. But in Engineering 17, he's going to allow you to use a calculator to solve them. I'm not. Okay? So that's why I'm only doing 2 by 2s and 3 by 3s. The idea is just to learn the technique. Okay. So I want to start with a simple one, and I don't have much time left, but let's try to do this. Let's see how far we can get in this one, because this one's actually a short one. The other one I have is much longer. I have 4 minutes. And I can't go too far over because I have an 11 o'clock class. All right, so I have 14 volts. I have a resistor. Another resistor. and I have a resistor on top. What can you say about the potentials at A, B, and C? Right, V sub A equals V sub B equals V sub C. We can also say that V sub D equals V sub E equals V sub F. Right, because they're just tied together by a wire. So this is what I'm going to do. So I have this circuit. This is what you would see in your a car, something. Yeah, you see this in a car. I took this out. I forget which textbook I took it out of. And it's a simple enough problem. You can set it up pretty quick. So I drew my picture. First thing I'm going to do is I'm going to assign currents. And it doesn't matter how I assign the currents. You choose whatever makes you happy, as long as you apply the rules correctly. Okay, so how I choose the current is completely arbitrary, but the physics is not. The physics will work. Okay. I do the Wheatstone Bridge problem in your notes twice. I'm going to do it one way, and then the second way you can look through the solution, and you'll see you get the same results. So I'm going to choose currents. I'm going to apply Kirchhoff's law, current rule right here at this junction. I'm going to have a current equal to I1 plus I2 going right here. I1 goes this way, and I2 goes this way. So by drawing that, I see that I depends on I1 and I2. And I1 and I2 are independent of each other. So that means I need two loops. I have two independent currents. I have two loops I have to write. Okay, I got to write two sets of equations. Okay, I'm gonna write the equations. I might go over a minute or two. What are my two loops? I can choose any three loops. There's three loops you see in that picture. I'm going to choose any two loops. Okay, I'm free to choose any two. I'm going to choose this one and this one. I didn't draw it big enough. I should draw. That's one of the bad things of not drawing your picture big enough. That wasn't big enough. Okay, my board isn't big enough. So on paper, when you draw this, draw them big enough. So by the way, the 1.2 ohm resistor is, let's say, your headlights. So let's start summing. Let me start here and go all the way around. I start here and I go from negative to positive. I have a 14 volt gain. And I said, so the current and this current going through here is clockwise. So I'm going to be summing in the direction of the current. Right, this is I, which is I1 plus I2. This is the advantage of using Kirchhoff's laws right away, because now I just writing everything in terms of I1 and I2. I get to this point, I'm going this way, because I'm going clockwise, and so this is 0.01 ohms. And then I have the 12 volt battery, which drops. Then the top loop, I'll start here and go around. Actually, let me start here and go around, because I want to put the 12 volts on the other side there. Let me start here and go around. So if I start here and go around, I'm going to go in the direction of I2. then I reach the battery, which is going to be, if I go this way, I'm going to get a gain. And then I go through, I'm going this way, I'm going against I1. If I'm going against I1, that's a voltage gain. So let me simplify these two equations. 14 minus 12 is 2. Let me simplify this one too. And I'm not going to write the units in, sorry. Okay, so here's what I'm going to do now. Everybody loves using substitution. These kind of problems, I really don't think you should use substitution to solve this problem. What I will do is I'm going to multiply the bottom equation by 11, and then I'm going to add. Okay, I'm going to multiply the bottom equation by 11. So 11 times 1.2 is 13.2. 13.2 plus 0.1 Did I do that right? These two will cancel because when I add these equations, I get 0.11 and 0.11. Somehow that looks strange. Hold on a second. Okay. And then 12 times 11 is 132. 132 plus 132 plus 2 is 134. Just check my math. And then I can solve for I2. Yeah, okay. Oh. No, that's fine. I'm going too fast. My notes say 9.0. I'm not sure if that's right. I think I have my answers backwards in my notes. Okay, is that okay then? This actually ends up being 10.1, I think. Yeah, this is 10.1. I have my answers backwards. Are we okay with that? Okay, and really that's it. That's all I have to do to solve the problem. So next time I will do a more complicated version. I think I have a typo in my notes. I'll double check that. Okay, I'm going to stop here because I have another class in 3 minutes. So I'll see you folks on Wednesday.